Hello, everybody, and thank you very much for providing me this opportunity to present my work to the PASIPHAE collaboration meeting that is currently happening in Oslo. I unfortunately couldn't be present there in person and therefore would be presenting my work through this pre recorded lecture online. I would like to thank the PASIPHAE collaboration for providing me the opportunity to work with some of you at IUCA and at Caltech in the past 2 years. And I would also like to thank Ashish Mahabar at Caltech, who was advising me in the past 1.5 months on executing this project. So, today I will be talking on automatically identifying artifacts in polarimetric images using deep learning techniques. To do so, I will be using the RoboPol image dataset that was obtained between 2013 and 14, and will be showing the promising results and the promise of this method for the upcoming WALOP polarimeter. So a typical artifact in a RoboPol image looks something like this, as seen in the green bounding box, where we see that it is a reflection from the bright stars on the left hand side, and we expect that these reflections are due to the interface between the two Wollaston prisms in the instrument. Now, the problem with these artifacts is that they can falsely be classified as stars by the source extraction algorithms, and false photometric results can be produced. Therefore, it becomes imperative for us to automatically classify the sources in an input image as artifacts and stars, and also to understand how much is the contribution of an artifact to the nearby stars. So there are two approaches by which we can solve this problem. One of them is a classical machine learning approach in which we would know what the features in our input data are and then appropriately select a feature extraction algorithm in order to extract those features. So for instance, if your input data has lots of lines or lots of features, then you would typically want to use an edge detection algorithm or a Huff transform from computer vision techniques, and then based on those extracted features determine which class does the input data belong to. But what deep learning really does is that it also helps us to automatically learn what these features in our input data are, and then based on those features provide an inference about which class does the input data belong to. Now, this is really helpful for us, especially in the case of RoboPol artifacts, where we really do not understand what features would the input data would look like. We may have a general idea of what they would be, but then if a deep learning model actually helps us to learn what those features are, then it provides us an end-to-end framework of automatically learning these features and performing the classification. So here is a typical RoboPol image which has been contaminated by artifacts. As you can see that there are several stars and artifacts in these images. Now, a typical challenge in RoboPol or in deep learning training is that we need to provide the deep learning neural network with a lot of labeled data sets. And to do so, for RoboPol images, we had to manually sift through hundreds of images and manually label where each of the artifact in the image belonged to, or which position did it was it found at. I would like to particularly thank Gina for sitting with me after office hours and manually labeling about 400 or 500 of these artifacts on 1 or 2 evenings. And it is really crucial that this step is executed with perfection, because your neural network will be trained on this data, and therefore if the data is having correct classification labels to it, then we can expect the neural network to perform correctly. So the artifacts were manually labeled by Gina and me, but to extract the stars wasn't a big task, because we already have a source extraction package called as extractor which helps us to do that. Now, I wrote an algorithm to automatically ensure that none of the stars lied in the regions that were very close to the bars or the mask of the RoboPol instrument, so that we did not have any of those kinds of features in our training data. Uh, so you can see that this is a nice collage of stars and artifacts which are present in the training data. And each of these stars and artifacts is actually an individual image of size 64 by 64 pixels, in which the entire artifact or the entire star fits in. And you can clearly distinguish with your eyes that stars are those objects which look nice and circular, whereas artifacts are those objects which have a nice streak looking nature to it. So now that we also have our training data, it's important to mention that our data, especially the stars in our training data, have a variation in their magnitude levels. Because if we had chosen only the bright stars in our source extraction algorithm, then what would have happened is, and what did happen initially, was that we biased our neural network to learn only stars of a particular magnitude or intensity level, and therefore stars of different intensity levels apart from that in the training data were falsely being classified as artifacts. Therefore, we ensured that we had stars from the brightest possible stars in an image to about the faintest possible stars in the image, and we ensured that we did not bias our neural network with training data of only a particular magnitude. Note that I also did not have the mapping for every star from its instrumental magnitude to the true magnitude, but that was not necessary for the purpose of training our neural network, and that is why you can see that this histogram is only of that of instrumental magnitudes. So as you can see from this plot, we had about 900 artifacts that we collected and about 820 or 830 cutouts of stars. And we use this as our training data. We assign the label of 1 to those images which were labeled as artifacts and 0 to those which were labeled as stars. Now, one of the problems with neural network training is that of overfitting. We do not want our neural network to learn our data so well that it provides a great accuracy only on the training data. But when provided with something that it is completely unknown, that is, some data on which the neural network was not trained, it can happen that the neural network will lose accuracy or will provide accuracy scores which are far lesser than what it was showing for training data. And when that happens, we see that the neural network was really overfitting to the training data. So one of the ways by which we can avoid overfitting, and which typically happens when you have a small data set size, is by augmenting the size of the data set. So by augmentation, what do I mean is that we can rotate or flip the input images which we have and increase the size of our data set by 2 or 3 times. By doing so, we not only increase the size of our data set, but we also make our neural network invariant to the shifts or rotations in our artifacts or stars in those 64 by 64 pixel bounding regions. So this is the neural network architecture that I developed. You can see that it uses three convolutional layers, three max pooling layers, and a dropout layer. The input is a 64 by 64 cutout, as we said, and the output is a classification score for the cutout to be an artifact. So if the input cutout is that of an artifact, then I would expect that the classification score, or I should say the prediction probability, would be close to 1. Whereas if it is that of a star, then I would expect this prediction probability to be close to 0. And you can see that the total number of trainable parameters was close to about 2 million, which is really large to even for three convolutional layers. And this model was inspired from the VGG16, or the Visual Geometry Group in Oxford, which was one of the first groups which implemented the use of convolutional neural networks for image classification. So this is typically how your neural network is trained, in which you provide it with some input images, and then it provides us an answer of what it predicts, or a prediction label, and then it compares what this predicted label is against the ground truth, and based on that it has a certain loss that we can define. So the whole idea of neural network is to optimize the weights of individual layers and the neurons in those layers, and making sure that we decrease the loss function at the output. So for instance, for a binary classification problem, this loss function is a binary cross entropy loss, as we would call it. And since since our output categories are only two, that is n is equal to 2, we would substitute n is equal to 2 here and solve our loss function. So there are several algorithms that are used to optimize the weights of the neural networks. And I wouldn't go into the details of them in this talk, but we use the ADAM algorithm to optimize the weights of our neural network. So all these algorithms which you can see here are simply based on the gradient descent algorithm, which has been used to perform backpropagation and optimize weights of our neural network or minimize the loss function. So here are the actual training and validation losses that we achieved. As you can see that close to the 100th epoch, both the validation and the training loss was close to zero point 0.1. What is interesting to see here is that our model is not overfitting because the validation loss is actually smaller than the training loss. So had the model been overfitting, our validation loss would have been far more than the training loss. And the same can be seen in the training and validation accuracy curves, in which we can see that the training accuracy is the validation accuracy is actually far more, or not far more, but more than the training accuracy, because of which we can clearly see that our model has not been overfitting, and it's really learning some of the general features of the input artifacts, the input stars which we have trained it with. So one of the good challenges now is to implement our data or implement our neural network on unknown data. And when I say unknown, what I mean to say is that I do not provide the neural network with ground truth labels. But I know that the input data is that of stars because I have individually checked for those images and their locations in the actual images. And what we see here is that most of the stars were not only correctly classified, but even their classification scores were close to 0%. Note that the classification score here is the prediction probability for the source to be an artifact. So for a star, we would expect the score to be close to 0. And as we see here, most of these objects or most of these stars have scores which are very close to 0, except for one which has been classified as an artifact with 66% probability. And you can see that in the second row and second column of this grid. Similar testing was performed on artifacts, and you can see that not only are all the artifacts correctly classified, but their probability or the classification probabilities were in the range of 90 to 100%. So for instance, if you see the second row and the last image in it, something as faint as that, you can barely make out with your eyes that there is a streak like nature which is present to that artifact, but it is extremely faint. Yet our neural network was successfully classifying it as an artifact with a very high prediction probability. So what we did was to plot a confusion matrix in which we see how many of these stars were really classified as stars, which I would call as true negatives, and how many of them were falsely classified as true as artifacts, and we would call them as false positives. And similarly, we do that for artifacts as well. And we see that only 5 of the input stars and input data were really only 5 of the stars were falsely classified as artifacts, whereas only 5 of the artifacts were falsely classified as stars. And it was a good test to see whether which of these were the false negatives. And you can see, so these are really in the ground truth for these objects was artifacts, but they were falsely classified as stars. And you can see that most of these objects are not only faint in magnitude, but also do not really have that streak like nature to them. Also in the last image, that the second row, you can see that there are many more objects which are present at the center of or close to the center of the cutout, because of which it could have been falsely classified as a star. Similarly, we have about 5 false positives, as you can see from here, and most of these stars, as you can see, were very faint in their magnitude range. So clearly, we see that the false positives or false negatives are not really as drastically bad as we initially would think them to be. Now, here's a very interesting plot which we made for our binary classifier, and that is the receiver operating characteristic curve. And the blue curve is that for our model, and the area under that is close to 1. Uh, An ideal ROC curve would be that which would start at the lower left end of this plot, go right up to the upper left region, and then move to the upper right region of the plot. So this is a plot showing the curve of the showing the true positive rate and the false positive rate at different values of the threshold. And the red plot is that of a random classifier, a classifier which does not perform well at all. So you can clearly see that not only is our classifier correctly classifying the inputs which are given to it, but it is also classifying, but it is also giving us a very good true positive rate and a very good false positive rate. So if we zoom into this ROC curve, we see that actually our threshold of 0.5, that is, if an object is above, if the prediction probability is above 0.5, we would classify it as an artifact. This threshold really coincides with that of 0.75, which in other words means that if even if we decided this threshold to be at 0.75, we would still have the same true positive rate and the same false positive rate. So our true positive rate is close to 97.5%, whereas our false positive rate is close to 3%. So here is a good comparison table I have made for the different architectures on which I tested. Although I showed you the final architecture, we also tested it for architecture involving only 2 convolutional layers and architecture involving 4 convolutional layers. And you can see that between the third and the fourth, between the second and third network, that is the network having 3 convolutional layers and 4 convolutional layers, there is not a big difference in its performance. But why did we choose the one with 3 layers is because the number of parameters to optimize in a 3 layered convolutional neural network would be far lesser than that in a 4 layered convolutional network, and also lesser the number of layers in your neural network, lesser is the chance that you would overlearn the features in your input data. So now that we have seen these numerical results, it is also a good idea to see what exactly is our neural network searching for in the input images. In other words, if we see a saliency map visualization, which is nothing but a representation of which regions in an input image of an artifact are mostly influencing the output classification score. So if we had to take a gradient of the classification score with respect to the different locations in the different pixel locations in the cutout, we would get a map something like this, where we would see that where if you see that all of these input images on your right are real artifacts, which have been classified as artifacts, and you can see that very interestingly, it is not even the center of these objects which the neural network is really looking for, but it's looking for symmetric regions on the left and right of the center as a saliency for the classifications label of an artifact. Here's something I would like to bring your attention to. If you see the image in the third row and the third column of this grid, you would see that there is a star at the upper right corner of this image and the artifact is at the bottom right. But the neural network has really only identified the artifacts region, but it has not really considered the star at the corner of the grid and the classification score, which in other words tells us that our neural network is really looking for features of that artifact or the streak-like features of our artifacts and not anything else while performing classification. So very recently we decided to test our neural network on 100 randomly chosen images which were not even a part of our training from the RoboPol dataset, and we plotted a histogram of the prediction probabilities. So out of those 100 images, we had about 90,000 sources uh, which were collected. And out of those, as we would expect, most of them would be stars. And we can see that clearly about 75,000 of those objects were classified as stars, and about 15,000 were classified as artifacts. But there was a very interesting peak in the region between 30 to 40% prediction probability. And what we did is we investigated how how many standard deviations above the noise floor were each of the objects in these different labels or in these different categories. So if we made some of those histogram plots, what we saw was that for the detections in the range between 30 to 40% prediction probability, most of these artifacts or most of these objects, which were still classified as stars, were having standard deviations above the noise floor of close to 3, or were between 3 and 7. Whereas for artifacts between 90 to 100% prediction probability ranges, most of these standard deviation values were above 10 and close to with a mean of, I think, close to 15. And similarly was the case for that of stars, which were predicted with a prediction probability of 0 to 10%. So that leaves us with a very interesting problem at the end, that if we can now map the instrumental magnitudes to the true values of the magnitudes, then we can actually get an idea of how significant are these detections and whether they really matter for our polarimetric measurements or not. Lastly, I would like to come to a very interesting development which we got to know last week at Caltech, and that is the use of something completely new in the world of deep neural networks called as tensor regression networks. So the Caltech Computing and Mathematical Sciences Department hosted a day-long session on tensor-based neural network learning. So in the upper figure, you can see that it's a traditional neural network in which after the convolutional and max pooling layers, you would normally use a fully connected layer, or you would firstly flatten the three-dimensional image, or the multi-dimensional layer which you have, and then pass it through a fully connected layer and produce a classification score. Now, the problem with this kind of fully connected layer is that firstly, we would lose all the multidimensional structure in our input data. And also, it would lead to a very large number of parameters to be optimized for. So typically, you would have a fully connected layer. Prior to the fully connected layer, typically you would have about 4,000 neurons in the flattened layer. And then you would use your fully connected layers, leading to very large number of parameters to be optimized for. What people at Caltech, especially the founders of the TensorLee Python library made by John Kosafi and Animashri Anand Kumar, who is a professor at the Caltech Computational Science Group, they have developed what they call as tensor regression networks, which essentially do not uh, flatten the layers after the convolutions, but they preserve the multidimensional structures by creating what they call as a tensor contraction layer, uh, which you can consider something as a layer which would have a low rank structure to it. And then when you multiply these low rank tensors with some weights which are optimized from a regression network, you would get an output. Now, why do all this? The whole purpose is to reduce the number of parameters that would be required to optimize your neural networks, and also to make sure that you reach your testing accuracy or your training accuracy in a very short period of time. So this is very useful when you want to implement your module on resources which are not as fancy as GPUs, and uh, mainly for those on mobile computing devices. So I actually worked over the weekend and tried to implement this on our network. And what we see is that by doing so, we actually reduce the number of parameters from about 2 million to about 27,000, and yet achieve the same performance in just 10 epochs as opposed to 100. So this is a very upcoming field in the world of deep neural networks, and I'll be happy to interact more with these people at the Astroinformatics conference that is happening at Caltech this week, and see whether we can really deploy this kind of a technique for the upcoming WALOP project. So the next possible map for the future work and my project would be to map these instrumental magnitudes to true magnitudes. See if we can implement transfer learning. That's a technique of using a pre-trained neural network to automatically find new classes of artifacts in our images, because right now we have only considered reflection artifacts, but we also would have dust donuts, satellite trails, and even cosmic ray hits. So see if we can now automatically identify new classes of these artifacts. and then finally develop or deploy the software for use in WALOP images. With that, I will come to an end. I think I have spoken for 25 minutes as I was requested for, and we could keep the remaining 5 to 10 minutes for questions and answers. So, thank you very much.